So welcome back. So at the end of the previous video we had finished proving that convergence of the sequence of vectors, vector convergence, implies that all of the coordinate sequences converge, implies coordinate convergence. What I want to now do is the other way round, see how if all of the sequences of coordinates converge, i.e. if you have coordinate convergence, that it implies that the sequence of vectors converges, it implies vector convergence. So if we do that then, I've put in the other arrow here, we'll have effectively proven that the two are equivalent, that convergence of the sequence of vectors is equivalent to convergence of all of the sequences of coordinates. So we'll start then with a sequence of vectors, and I've rubbed the fact that this sequence of vectors converges to some limit vector out, because we're not starting with that assumption. And then of course we will have all of the corresponding coordinate sequences to our sequence of vectors, and we're starting with the initial assumption that all of these coordinate sequences converge. So we'll call the limit of the first coordinate sequence L1, we'll call the limit of the second coordinate sequence L2, all the way down to the nth coordinate sequence, and we'll call its limit Ln. We now want to show that our sequence of vectors converges, and that it converges to limit vector that you build by putting together all of the limits of the coordinate sequences, i.e. the first coordinate of our limit vector is going to be L1, the limit of our first coordinate sequence, second coordinate is going to be L2, the limit of our second coordinate sequence, etc., all the way down to the nth coordinate of our limit vector being Ln, the limit of our nth coordinate sequence. So applying the definition then, to prove this sequence of vectors converges to this limit vector that I will call, of course, the L limit vector, I need to show that if I take any epsilon greater than 0, that I can find a vector in my sequence of vectors, and I am now going to change to using different letters so that we don't get confused. So I will now try and use little m and big M rather than little n and big N, so that we don't get confused with the little n that is denoting the dimension of our space. So I need to be able to find a big M such that for all vectors in my sequence from that big M onwards, so for all little m greater than or equal to big M, the distance between the vector xm and my limit vector L is less than epsilon. So how am I going to do this? Well, of course I'm going to use the fact that all of my coordinate sequences converge to the coordinates of this limit vector, or this hypothesized limit vector. So what I know is because all of these sequences are convergent sequences of real numbers, they obey the epsilon definition, so I could certainly take this epsilon and I could find for each one of these sequences a corresponding big M, such that from that big M onwards all of the terms of the sequence are within epsilon distance of the limit. And for each one they'd have a different big M, but I could just take the maximum of those, and that would be a big M that would then work for all of them. That would almost get you there. It wouldn't quite get you there. I know where we're going, and I'm therefore not going to use epsilon. Instead, I'm going to use the epsilon, but I'm going to divide it by the square root of n, where n is the dimension of my real n space. This is the thing that I need to get all of these sequences within in order for this to work out. And you see now why I wanted to change notation, because having this n here is going to get really confusing if we had also got n meaning the term of the sequence. So it's better that we've changed notation so that now little n has only one meaning, which is the dimension of my space. So that's some positive natural number. You can take its square root, that will be some real number, and then I can take whatever epsilon is and divide it by the square root. So I can certainly do this, and this is what I'm going to apply to the epsilon definitions for the convergence of these sequences. So I'm going to get all of them within this distance of their limits. So applying the definition then, there will be an M1, a big M1, such that it and all the terms beyond it are within epsilon over the square root of n distance of L1. Similarly, for this second sequence, there will be a big M2 such that at that term and for all terms beyond it, they are within this distance of L2. And I'll do this for all of the coordinate sequences down to my nth one. There'll be an M big N such that at that term and for all terms beyond it, they are within epsilon over the square root of n distance of the limit Ln. Now there's no reason that m1, m2, all the way down to mn are all the same. They could all be different. So now I need to find a big M that works for all of them. That big M will be the maximum of them. So I'll make my overall big M the maximum of big M1, big M2, all the way up to big Mn. Then if I go to that big M in all of these sequences, then it and everything beyond it will be in the tail end of the sequence, i.e. will be within epsilon over the square root of n distance of their limits. And the reason I need to do this is because now I want to go up to my sequence of vectors and use this as the big M for my sequence of vectors. So I need all of the coordinate sequences to be within epsilon over the square root of n distance of the corresponding coordinate of the limit vector. So now my claim is that this big M works, i.e. that if I take any little m that is greater than or equal to big M, that the distance between my vector x little m and my limit vector L is going to be less than epsilon. So let's think about what this norm is now. So again, we need to remember the definition of the Euclidean norm. But firstly, let's just write this vector out properly. So it's the norm of, and then this vector written out with all its coordinates is here. This vector written out with all its coordinates is here, and then we've subtracted the two from, we've subtracted this one from this one, so we've got x little m1 minus L1, x little m2 minus L2, all the way down to x little mn minus Ln. So let's understand why this is going to be less than epsilon, so just write it out. The definition of the Euclidean norm is then the square root of the sum of squares of the coordinates of this vector here. So here's the first coordinate, xm1 minus L1, then squared, plus the second coordinate squared, so the second coordinate is xm2 minus L2 squared, plus all the way up to the nth coordinate, xmn minus Ln squared. So we need to show that this thing is less than epsilon then. So what we know is something about all of these bits here, the coordinates of this vector that we're taking the norm of. Because remember, little m is greater than or equal to big M, and big M was the maximum of all of these m's here, big M's here. So little m is going to be in the tail end of all of these coordinate sequences here, i.e. if you look at the modulus of xmi minus li, where I've left I general, it could be any one of these coordinates here. So it could be 1, it could be 2, all the way up to n. You can fill in whatever you like there. It will be less than epsilon over the square root of n. So what I now just need to do is square this inequality. Both things are positive, so the inequality will remain true. And then I'll have something about all of these squares that I've got underneath this square root here. So as I say, I'm going to square this inequality. So this thing squared will give me xmi minus li. Again, we're doing this for a general I. You could have any of the coordinates there, so 1, 2, all the way up to n. This thing squared is going to be less than this thing squared, which is epsilon squared over n. And that's true for all I is equal to 1, 2, all the way up to n. So now I can conclude that this thing here is this inequality with I is equal to 1. So that thing is less than epsilon squared over n. This is I is equal to 2, so this thing is less than epsilon squared over n, and it continues on all the way up to this one. I know that this one is also less than epsilon squared over n, and therefore I know that the sum of them is going to be less than epsilon squared. So I've written it out then. This sum of squares, which is the sum of squares that's there, so xm1 minus L1 squared plus xm2 minus L2 squared plus all the way up to xmn minus Ln squared, this must be less than epsilon squared because each of the n things that's being added together here is strictly less than epsilon squared over n. Now, of course, what I'm going to do is take the square root of both sides. Both sides are non-negative, so I can take their square roots, and I can take the square root without it affecting the inequality. So take the square root of this and the square root of this. So I've put in the square root sign over the sum of squares here, and then I've square rooted epsilon squared to make it epsilon, and I've now got the inequality that I wanted to show, which is that the norm of this vector here is less than epsilon, meaning that the distance between my vector xm and my limit vector L is less than epsilon if I take m, little m, greater than or equal to this big M that I showed you how to construct. So what I have shown you is that whatever epsilon you take, I can find you a big M in this way, such that for all little m that is greater than or equal to big M, the vector x little m will be within epsilon distance of the limit vector L. So the sequence of vectors then does meet the criterion for convergence to this limit vector which we built out of the limits of the coordinate sequences. So yes, if the coordinate sequences do all converge, then the sequence of vectors overall converges, and it converges to what you'd expect it to converge to, which is the vector built out of the limits of the coordinate sequences. So this is a very good way to find out whether a sequence of vectors converges. So just look at all of the coordinate sequences that are then just sequences of real numbers. If all of those converge, then the sequence of vectors does converge, and it converges to the vector that you build out of the limits of the coordinate sequences. So we have shown then the bidirectional equivalence. Convergence of a sequence of vectors is equivalent to convergence of all of the coordinate sequences. So we'll have a break here, and in the next part I'll talk a little bit about the algebra of limits for sequences of vectors, and this follows very nicely from what we've just shown about sequences of coordinates.